Hey everybody. Today we're going to cover a quite interesting and fundamental topic in robotics called simultaneous localization and mapping. Now, the purpose of this lecture is not to really get you too much to grips with the math behind it, although a lot of it I think will have been covered in the filtering and state estimation lecture that you had with Dr. Rossman. But the purpose of today's lecture is more to show you how SLAM could work. It will present one algorithm for how SLAM can be done using a robot. Now, the first question, I guess, is what is SLAM? So you've looked at the localization problem, right? And the localization problem was one in which you had a robot that was put into a known map. Okay, in that known map, it could then take observations and try to figure out where it is. Okay, and this was done iteratively. So as the robot moved around, you were given the control signals, you were given a motion model, and you would take observations and transform them according to your observation model. Okay, so SLAM is a quite similar problem. Simultaneous localization and mapping has localization in there, right? So if you know how to do localization, you're halfway there. The difference with SLAM is that you don't have a map. So what you've got now is you've got the control and the observations, and what you're trying to do is both create a map and localize yourself in that map. Now, in principle, that sounds pretty hard, right? It sounds a lot harder than localization, because with localization, you had a map, so you just had to try and correlate to that map. So in theory, this sounds a lot harder. But in practice, it's actually really similar to localization. It's not such a huge difference between the two. When you did localization, the primary technique you explored was particle filtering, right? And the whole point of using particle filters was that you could model any arbitrary distribution that you're drawing from. So I'm just going to quickly recap particle filtering, just because we're going to use it quite heavily in this lecture as well. Now, the important thing about particle filtering is that every particle is a hypothesis. When you're doing localization, you had this, you could sort of visualize it as you're just chucking particles all over your map. Okay, so you just put a ton of particles everywhere in your map. And as you moved around, you found that those particles disappeared or congregated or something like that. But it's more general to say that each particle is a hypothesis about our state. Okay, if you're doing localization, each particle was a hypothesis about our position. So we chucked those particles all over the space. But what we were really doing was saying, I don't know where I am. So when I construct a hypothesis of where I am, I'm going to have to basically evenly distribute that hypothesis, or those hypotheses. There's going to be a hypothesis for where I am randomly in the map, and there's going to be tons of these hypotheses. So basically all that ends up happening is I've got particles all over my map. Okay, then what we do is we say, okay, fine. Each particle represents a hypothesis. So let's evaluate each hypothesis. So what we do is we say, okay, for every particle, take an observation and check how well the observation correlates with where we expect that particle to be. Okay, if it correlates badly, so if, let's say my particle is a hypothesis that's right next to a wall, but I take an observation and I don't see a wall, then what I do is I give that particle a very low weight. Okay, when particles or hypotheses correspond really well to my observations, then I'm gonna give them a very big weight. And what do I do with that weight? I then resample in a weighted manner from those particles. So the ones that correlated well to the observations have a very good chance of being selected, whereas the ones that didn't correlate at all, those will basically get killed. So when you were doing localization, you followed these steps in particle filtering. What you had to do was just create n particles. As I said, just chuck them randomly throughout the space. They represent your position and orientation. Then, iteratively, you apply the control that you know you applied. So maybe you said the robot walked one step forward. So then you apply your motion model to move every particle one step forward. Okay, you take an observation and you see how well the particles' hypotheses or the new positions after the motion has been applied correspond to what the observation is. You apply those weights and then you resample biasing towards high weight particles, meaning that you're now going to fundamentally kill off the particles that don't correspond well with the observations, and you're going to end up with a lot more particles being congregated around the points that correlated well to the observations. Okay, so an important thing about it is that when you apply your motion model and your observation model, these things have noise in them. So what happens is that your hypotheses that are created by applying your motion model in terms of moving around the space will end up dispersing, right? Because let's say I think I'm at position 5, 2, and then I say I took a step forward. So maybe I should be at position 6, 2 or something like that, right? That's a pretty arbitrary example, but what will actually happen, because I'm operating in the real world, is I might end up at 5.92 or 6.22, meaning there's some noise in how I moved. Okay, so when I apply the motion model, I apply them to every particle by taking a draw from the motion model. So if I've got like 10 particles in the same spot and I apply my motion model, I end up with 10 particles that have moved forward by a step, but because they've applied different amounts of noise, they're not in the same spot anymore, right? Now, why do particle filters work so well? The main reason is they're sort of implicitly keeping track of the temporal correlations. So basically, what they're doing is that they're kind of going, okay, since this particle keeps moving based on the motion model, I'm keeping track of everywhere that it has been before. And then through the number of particles that are in any particular space, I'm keeping track of how well it has correlated in the past to all the observations that I've taken previously. Okay, so fundamentally what that means is that I don't have to base my estimate of where I am on any individual observation or individual application for the motion model, because in this particle I've encoded the entire history implicitly. I mean, there's no data actually there, but just by having so if I've got say 7,000 particles in one spot, what I'm saying is that those particles, the fact that there's 7,000 of them means that in the last observation it correlated incredibly well with what I expected. Okay, so I'm and then that last observation encoded that in the previous observation it correlated really well. So it means over time I'm keeping track of all of this without actually having to keep track of it, which is incredibly powerful. Okay, so for SLAM it's quite similar. We have the same problem basically. We've got an individual observation and an individual control input, and we're trying to figure out where we are and what the map looks like. You can't really do that. What you have to do is base it on the entire history of observations and control that we applied, right? So we use particle filters because they're going to do basically the same thing they did in the localization example, and they're going to keep track of history for us without any real effort. Okay, so we're going to look at SLAM using landmarks, which is a very common way of doing SLAM. And the landmarks in our environment can be any visual feature, right? A common choice is corners, but I mean it could be anything that you can observe and that it's easy to note that you've observed before, right? So like if you've got like another sort of almost cheating kind of technique people use is to put QR codes all over the place. Which they are called AR tags, and then when you observe these AR tags, you can say, "Oh, that's a feature that I've seen before," and so you can kind of close your SLAM loops. Okay, so but for this discussion, we're going to use corners as landmarks. Okay, so the important thing about doing SLAM versus localization is that we don't have a map. So where previously every particle contained a hypothesis about the position of our robot, being its x, y, and theta. Now every particle is going to have to contain a hypothesis about x, y, theta, and the map. Okay, so that also means that our update is affected as well, right? Previously, our updates would update the x, y, and theta of the robot, right? When we applied our motion model. Now every update must update both the position of the motion model and the map of the particle. So it we'll do a sort of iterative thing. We'll use our motion model to apply our control in the space. So if a particle said it was at 6.2 and we took a step forward, we can end up at 6.92 or 7.12 or even 7.2. And that'll allow us to do the position updates. Then, based on our observation, we'll update the map that we currently have and the weight of that particle. Okay, so what does our algorithm look like? So the first step is quite similar to the localization example. We just create n particles which represent hypotheses of our position, orientation, and the map. Okay. Then what we do is we iteratively update the positions and orientations of the particles based on the motion models. We take an observation. We update the map based on the landmarks we see in the observation. And we update the weight in the particle based on how well the observation correlated with the map. Then we resample exactly how we sampled in the localization example, right? Ones with high weight have a bigger chance of being selected, and ones with lower weights have a smaller chance, and we can select the same particle multiple times, fundamentally cloning particles. Okay, now don't worry if you didn't follow that particularly strongly. I'm going to go through what each of those steps actually looks like. Okay, so the first thing is we have to create n particles. So this part is really easy. So since there's no map, right, there's no reason to distribute our particles evenly over the positions. So you remember in localization, we said, chuck your particles like all over the map. Try to put particles everywhere in the map, right? But now you don't have a map. So we just put all our particles at 0, 0, 0. Okay, because it doesn't matter. There's no actual global concept of our position, right? Our position is always relative to our map, and we don't have a map. So we just put all the particles at 0, 0, 0. And since there's no map yet, they all just have an empty map. Okay, so you just have like a ton of particles that look identical. And that's all that's happening here. Now, what happens next is we then gonna take observations to construct our map, and we're gonna apply our motion model to decide how to move. So the first thing is we're gonna apply the motion model by taking a draw from our distribution based on the control input we applied. Because remember, our motion model has noise. So we'll have, like every particle will now be at a different x, y, and theta based on what draw we got from our motion model. Okay. So let's look at an example of how this is going to work using corner landmarks. So the first thing is we've got an agent at position 0, 0, 0, and we've got this map, right? Now, this is just for the example. In practice, we don't actually have a map. This is sort of what the human sees rather than what the robot sees. The robot sees nothing right now. Okay. Then the robot will take an observation and it'll see some corners. Okay. So what we do is we say, okay, given that I'm at 0, 0, 0 and my line of sight to the corner is at something like, I don't know, 40 degrees and it's 3 meters away. That means I can use some transformation to figure out exactly where the landmark is. Okay. But because my observation model has noise, that corner point will actually have some variance. What do I mean by the observation model has noise? So let's say I'm using something like a camera, maybe a Microsoft Kinect or something. Then I'm saying I see this corner 2 meters away, but it may not actually be 2 meters away because my camera has some noise in it. Okay, so that means I'll have to put together sort of a distribution of where my where I think my corner is, and fundamentally I'm going to use a Gaussian to represent this. Now this is actually going to be a multivariate Gaussian. I've just drawn a univariate Gaussian there because it's easier to look at. So fundamentally picture that as being in multiple dimensions, right? Because I'm uncertain about both the x and the y of this landmark, right? So what the robot sees is it fundamentally sees like these 4 landmarks, okay? And then it just stores that as the map, okay? But in that map, it'll store the positions as well as the variances of each landmark. So it's going to say maybe, I think this landmark is at 4, 7, and I am this sort of certain. Okay, so our map only contains corners in this example. There's no walls or anything. We just have the 4 landmarks in this case. Okay, then what we do is we move along, we apply some control, and we draw a sample from our motion model. Move the particle along so that now maybe, previously my particle was here and now it's moved here. Okay, so we've moved along based on our motion model. But this is just an example of a single particle. Every other particle will be sort of around here, but kind of dispersed because the motion model has noise in it. Okay, then we take another observation. And again, we do the transformation to get the position of the landmark. But now we say, okay, look, this thing maybe is at, I don't know, 10 degrees. But I am at 20 degrees, so it's like 30 degrees. And I'm not at 0, 0, I'm at 5, 9. So we'll have to use a transformation matrix to figure out where the landmark actually is versus where it is in our observation, right? And we end up with some set of landmarks that we're observing now, say these 3, right? So the next question we ask in order to update our map is, how well do the landmarks correlate to existing ones? So what we do is we use the mean and variance of the landmark and a threshold probability to indicate whether it's the same landmark. So let's say we see this landmark, right? And we're comparing it to the landmark in our map that's closest to it. And we say that, oh, it looks like it's over here on the distribution, right? Let's say this is the position we thought the landmark is at, and when we see this one, we see that actually it's this far away, and we say, okay, well, look, that's pretty close. I mean, that's within some reasonable range. So we have to define like a probability threshold to say what closeness means. But in this case, let's say we're within our threshold. In this case, maybe we're saying it's within a 60% probability that it's the same landmark, right? And if we find that it's within that threshold, then we do an update using a Kalman filter to update the variance. Why do we do that? Well, basically, we thought there was a landmark here. And then when we took an observation, we found the same landmark here. So we're going to end up with a new mean that's somewhere around here, and maybe a much smaller variance because we've now seen 2 observations, and so it's slightly more certain that there actually is a landmark there. Okay, so remember, the variance represents our uncertainty, and the more observations we take, the thinner that is going to get. So the smaller the variance. And the mean represents where we think that landmark is. Okay, so again, if we think we've seen the landmark before, we update the variance. So for these 2 observations, we're going to find that they're close to existing landmarks, and we're just going to reduce the variance on those landmarks within this particle. For this new landmark, though, we might compare it to every landmark we've seen before and find that, hey, it's nowhere near the threshold for acceptance. So the likelihood that this landmark is ridiculously low based on our normal distribution, and it's incredibly low for this one as well. So this one must be a new landmark. So if it's a new landmark, we just add it to the map with the variance from our observation model. Okay, so now we've got a map with 5 stars in it. Now the next sort of important part about particle filtering was we had to figure out the weight of the particle. When we did it for the localization algorithm, we just based it on how well the observation correlated with the map, right? And we're going to do the same thing here. Basically, when we update the weight of the particle, we look at only the landmarks that correlated with existing landmarks. Okay, so if we look at this one here, we said it did correlate, right? But it didn't correlate exactly. It wasn't like directly on top of where that landmark's expectation was, right? So if this was, say, at the 90% probability, then we're going to say, okay, that's a 0.9 over there. Or that one, sorry. And maybe that one was at a 0.8. So then what we do is we say, okay, let's just multiply those probabilities together, and we end up with a 0.72. Okay, so we're saying the weight of that particle, or the probability of that hypothesis in total, is 0.72, because it thought they were going to be a landmark here and here. And then they were, but they were slightly not where the model said they should be. So the model is slightly less likely because of that fact. Okay. In practice, you end up using log probabilities because the probability numbers can become incredibly small, right? When you're using this algorithm, you tend to want lots of landmarks. You want to see multiple landmarks on each observation. So when you multiply all of these probabilities that are not one, you eventually get very small numbers, and you can have trouble representing these in a computer. So you just use a log probability to get around that problem. But so yeah, now we've got to wait. And so if we have multiple particles, each of them is going to end up with different probabilities of their map being true based on the where they think the observation is, right? So once we've got all our weights, we can resample, and this one we found that the landmarks correlated really well. So we end up with like quite a big particle. And maybe some other ones didn't correlate particularly well, so we get very small particles. And then when we resample, we're very likely to sample this one multiple times, and we end up with lots of particles on the same spot, which will disperse because of the motion model. And yeah, and we just keep doing that, and eventually we end up with a map of all the particles in the with a map with all the landmark hypotheses in it. And like as you go along, just bad hypotheses will die and the good hypotheses will fundamentally reproduce, if I can put it that way, because they'll just get drawn multiple times. Okay, so you'll notice I didn't go heavily into the math, and I think that's not really the purpose. That's something you guys can look at yourself if you want, but it's not particularly complex. But the important thing was just I want to show you guys at a high level what SLAM is, how does it go about actually finding a map, and an example of how it works. There's lots of different SLAM algorithms. Some use landmarks, some don't. This was an example of how a landmark-based SLAM algorithm exists. So this is actually the last lecture in the course. So yeah, I hope you guys had fun with us in the theory parts of the course, and in terms of following the lectures. There's a lot of practical to come, so I hope you're all excited about doing amazing things with the robots based on these algorithms. Thanks.